So we have been talking about soil reinforcement, Unit 5. Whenever we talk about the soil reinforcement, three things come in our mind. Soil, reinforcement, and facing unit. These three components come in our mind. Suppose you are going to construct the retaining wall, soil reinforced retaining wall. So in that wall, what you have to use? You have to use the soil, you have to use the reinforcement, you have to use the facing unit. So in the previous lectures, what we have discussed, we have talked about what are the various components of the reinforced soil, what should be the properties of the soil which you are going to use as a fill material. We have talked about the properties of cohesionless soil, that is the phi soil. We have also talked about the properties of C5 soil, cohesion frictional fill. What should be the properties of C5 soil? We have also talked about the cohesive soil. In addition to that, we have also discussed about what are the various reinforced materials available in the market which can be used for the preparation of reinforcing element. Reinforcing element means anchor, strip, geogrids. Likewise, many we have discussed earlier in earlier lectures. We have also talked about we have also talked about the facing unit. We have talked about the soil, talked about the reinforcing element. We have also talked about the facing unit. We have also discussed about the advantage and disadvantage of facing materials, uses and advantage of reinforced earth structures, that also we have discussed. And then in study lectures, we also started the design consideration of mechanically stabilized earth. Mechanically stabilized earth wall means reinforced soil retaining wall, we can say, right? Mechanically stabilized earth is a very generalized word, right, which can be used for the reinforced soil wall, whether it is a retaining wall or the dam. So mechanically stabilized earth is nothing but soil reinforced wall. So this what should be the design steps? The 7 steps are there. We have talked about the 4 steps. The remaining steps we shall discuss today. So whenever we talk about the design considerations, we have to know only about the procedures. What are the design components we have to carry out? We have to know what are the various design components for the design of mechanically stabilized earth wall or reinforced soil earth retaining wall. Reinforced soil retaining wall. So first topic, that means step 1 in the design, we have discussed in the study lecture, is establish project requirements. Project requirements means the geometry of the wall, wall height, wall better. Wall better means whether wall better means inclined wall or the vertical wall. Back slope, toe slope, right? Loading conditions, whether the soil surcharge, live load, dead load, seismics, all these things, performance criteria. That means which design code we have to follow. What will be the maximum tolerable differential settlement? The maximum tolerable horizontal displacements, design life. Normally we design the structure for 75 years. And then second step, we have talked about the establish project parameters. Project parameters means we have to know the engineering properties of the soil, that is the cohesion, angle of shear resistance, density of the soil, reinforced wall fill, right? Reinforced retained back fill. This we have talked in the step 2. As far as the step 3 is concerned, estimate wall embedment depth and reinforcing length. And the fourth component we have talked about the define nominal load, live load, dead loads. What should be the Nominal load means minimum load which we have to consider in the design. So we shall see here the swell reinforced wall, the swell reinforcement, how it is laid, how it is spread at the time of construction. This figure also I have shown you in the beginning. So now once again I would like to tell you the minimum embedment depth, right? Suppose we talk about the yesterday I also talked about the estimate wall embedment depth and reinforcement length. Once again I would like to repeat that the topic. What do you mean by the embedment depth? Minimum embedment depth. Minimum embedment depth means, suppose this is the retaining wall. You can see the first figure and second figure. Two figures are there. D is the depth of the foundation from the ground surface. What's with the depth? Embedment depth means what's with the minimum depth of the foundation for the swallowing force retaining wall. Here it is written that minimum depth is equal to 2 feet. And in second figure, suppose you are going to construct the retaining wall where the ground is having the sloping, ground is inclined, or ground is having sloping surface. So in that case, what we have to do, you can see in the second figure, the DS is there. DS is the minimum depth for slope toe, minimum depth for the slope toe. So you can see the dotted line, the solid line, the slope line has been shown. So from the toe or leveling pad means that the bottom part of the foundation we can say. So DS, what is DS? What is DS? Depth of the foundation. Minimum depth for horizontal slope. Minimum depth for the DS is the minimum depth for horizontal slope, that is which is given in the first figure, and minimum depth for the sloping toe or the sloping surface, that is also given here, right? In the figure it is clear. And you can see the horizontal distance, the 4 feet we have to go for the 4 feet is also given in front of the facing part, that can be used for the road construction, for the movements, for maintenance purpose, that I will tell you. See, the depth is required. If you are not going to, suppose you are going to construct the foundation on the ground surface, the foundation not be strong. Definitely you have to excavate the soil and then you have to start the construction of the structure. So here structure is reinforced soil structure. So based on bearing capacity, settlement and slope stability consideration, we have to decide the depth of embedment. Larger depth required due to shrinkage and swelling. Suppose below the ground surface, black bottom swell is there, which is definitely having the shrinkage and swelling nature. So that also we have to consider. That also we have to consider at the time of deciding the depth of foundation. We have to start from the deeper depth, larger depth, where the shrinkage and the swelling type of swell is not available. Here you can see larger depth required due to shrinkage and swelling of foundation swell. Seismic activity, if there is any chance of a scoring, that also you have to keep in your mind, and accordingly we have to decide the depth of foundation. Frost susceptible swell, up to what depth the swell is going to become frost or ice, right? So below that only we have to start the construction of the foundation of the swell reinforced structure. Next we can say, yesterday also I talked about the minimum depth of embedment. What is said that minimum depth is 2 feet here, except for the structure founded on rocks where no embedment may be used. What does it mean? That means suppose you are going to construct the structure on the ground surface, and the ground surface, below the ground surface also soil is there. In that case, the minimum depth of embedment, the minimum depth of embedment means minimum depth of foundation you have to have 2 feet, right? But if suppose your ground surface is itself rock, in that case you can start from the ground surface itself, It is not required to excavate the rock. Similarly, a minimum horizontal bench 4 feet, as I have told you in the previous slide, wide from the face wall, facing unit 4 feet wide we have to provide. You can see in the figure 4 feet minimum wide the platform we are also going to construct. Is written there 4 feet wide from the face is provided in front of walls founded on slopes which provide resistance against bearing failures and to provide access for maintaining inspection. So suppose you are going to construct this structure where sloping ground is there, inclined ground is there. So you have to construct one platform also in front of the facing unit so that it will what it will do? It will provide the strength to your reinforced wall structure, right? As well as that 4 feet platform can be used for the inspection, right? Time to time you can go through that along the 4 feet the wide road you have constructed. You can move there so that you can check that any uh, problem is there in the structure or not. That also you can check. See, minimum reinforcement length I told you. You can remember the first diagram of this PPT. The minimum reinforcement length. Suppose your your width of the reinforced soil structure is 4 feet, for example, 4 feet. And if you are going to use the small length of the reinforcement, suppose you are going to use the iron rod, your width of the reinforced soil structure is 4 feet, and you are going to use the small size, small length 2 feet. 2 feet, again 2 feet, right? This is not good, right? So what should be the length of the reinforcement which you are going to speed or which you are going to lay down on the surface of the reinforced soil wall. That means at the time of construction, what we do? We normally used to carry out the first layer of soil, then reinforcement, then second layer, then reinforcement, right? So the width of the width means here the length of the reinforcement should be the complete width of the minimum complete width of the retaining wall. If you are going to use the small size of the reinforcing element, in that case, the structure will not be strong. That is the problem. So what it says that less length of soil reinforcement will cause decrease in internal strength of reinforced wall. So minimum reinforced length 0.7 h we have to use, where h is the height of the design height of the structure. How much height you want to construct the reinforced soil retaining wall, right? So length by height ratio is 0.7. That means length is equal to length of the reinforcing element will be 0.7 h. Similarly, structures with sloping surface surcharge fields. That means what? We have already discussed the earth retaining wall, right? We have also talked about the earth pressure in 5th semester. Sloping surcharge, right? Uniformly distributed surcharge. The sloping surcharge means what? Sloping surcharge means suppose above the retaining wall or back side of the retaining wall, the sloping ground is there. Sloping ground is there. That sloping ground is going to work as a sloping surcharge fields. So in that case, we have to use the length of the reinforcement 0.8 h to 1.1 h. You should not have any doubt. So structures means reinforced wall structures or reinforced wall with sloping surcharge field. Sloping surcharge fields are behind the reinforced retaining wall. The filling of material is inclined, right? Right, which is going to definitely act as a sloping surcharge fields. Or if suppose concentrated load is there, in that case we need the longer reinforcements for constructing the earth retaining structure, that which varies from 0.8 h to 1.1 h. So this topic also we discussed yesterday. So now we shall go for the next points. The next point is the fifth step for the design of mechanically stabilized earth. Whenever I talk about the mechanically stabilized earth, you must have in your mind that the soil reinforced wall or reinforced soil wall, right? It is a generalized name. Mechanically stabilized earth is a generalized name. So the fifth steps for the design of mechanically stabilized earth is the evaluate internal stability. The very important parameters. What parameters we have to evaluate for the internal stability of your mechanically stabilized earth or soil reinforced retaining wall. See, 2 points are there. The first point is sometimes what happens, internal failures occurs. Once you are going to construct the retaining wall, soil reinforced retaining wall, there is a chance of two types of failures. Internal failures. One failure, suppose you have designed the reinforced retaining wall in such a way which is not capable to take the load or the which is not capable to take the load available behind the retaining wall. That means what? Suppose inclined surface which is the length of the inclined surface is very large, and accordingly you have not constructed the retaining wall to control the landslides. So in that case what will happen? The failure will take place. Your retaining wall will collapse. So what type of failures are going to occur which comes under the internal stability? The first one is the tensile forces in the inclusion. Inclusion means whole materials. The whole soil reinforced retaining wall becomes so large that the inclusion elongate excessively or break, leading to the large movement and possible collapse of the structure. This mode of failure is called failure by elongation or breaking of the reinforcement. That means your whole retaining wall is going to collapse due to tensile forces. Or we can also say that like rigid retaining wall, shear force is going to work. Because your designed load is designed, you have to design whatever you have to go to design the retaining wall. You have not designed the retaining wall according to the load coming on that retaining wall. So in that case, what will happen? It will crack, right? The whole the retaining wall will fail. Second type of failure is the tensile force and their reinforcement become larger than the pull-out resistance. What does it mean? Already I have discussed with you pull-out test. Pull-out test is nothing but it is the grip or internal grip, we can say, the grip between the soil and the reinforcing element. If you are going to carry out the experiment, prototype experiment, that means what? You are going to prepare one model where you are going to fill the soil, first layer, second layer reinforcement, third layer soil, second layer reinforcement, next layer reinforcement, next first again soil. So what? And then you are going to pull the reinforcement. Definitely there is a grip between the reinforcing element and the soil. There is a grip, frictional grip is there. So how much load you are going to apply, right? If see the maximum pull out load also we have discussed earlier. So maximum pull out load, what it says that if the tensile force in the reinforcement become larger than the pull out resistance, that the load which is generated due to the grip between the soil and reinforcing element, that is the pull out resistance. And the tensile force resistance in the reinforcement means the reinforcement which is going to generate in the reinforcing element. So if there is tensile force in the reinforcing element is more than the pull out resistance, in that case this type of failure is also going to occur, which is called as failure by pull out. So these two types of failures are normally found in mechanically stabilized earth wall. So how we can control the internal, how we can evaluate the internal stability? These things we have to evaluate. So for the we have to do, you can see for those problems, we have to select the suitable type of reinforcement, right? We have to also define critical slip surface. Critical slip surface, we have discussed critical slip surface in case of slope stability. So what it said that the critical slip surface in a simple reinforced soil wall is assumed to coincide with the locus, means focus of the maximum tensile force in each reinforcement layer. These two should be taken care of. The next, define unfactored loads. So if you are going to consider all these parameters, there is no chance of the internal stability failure. So unfactored loads include vertical earth pressures, live load surcharge, earth surcharge, water pressure on your retaining wall, seismic, vehicle impact loads should be properly evaluated. Otherwise, this will cause the failure of your structure, which comes under the internal stability failures. The next is the established vertical layout of the soil reinforcement. See, whenever we talk about the vertical reinforcement, that means the layer of reinforcement you are going to put in vertical direction, in upward direction. First, you are going to put the first layer of the reinforcement, then soil, then second layer of the reinforcement, then soil, again next layer of the reinforcement, like that in vertical direction. So what it says that use of a constant reinforcement section, whatever the reinforcement you are going to use, that reinforcement should have a constant section, constant thickness, and a spacing for the full height. A spacing should be properly maintained. Suppose 15 centimeter, 15 centimeter, 15 centimeter in vertical direction. Not 15 centimeter, again 20 centimeter, 25. It should not be like that. And the next point is pull-out test. Each layer of reinforcement should be checked as pull-out reinforcement for the every layer. That pull-out test should also be carried out. Check connection strength. See, connection strength means what? You are going to join or connect one reinforcement to the other reinforcement by some connecting, by some the materials which is called as bolt or tie, right? So that strength should also be checked. So if you are going to control these parameters, there will not be chance of the internal stability failure. See, the next design parameters evaluate external stability. So internal stability, what we have to do? In case of external stability, there is a chance of base sliding, right? Sliding on the base. How sliding can take place? You are going to construct the retaining wall in Jammu and Kashmir, in hilly area, to control the landslides. Suppose on the retaining wall, if horizontal or vertical pressure generated behind the retaining wall is more, in that case what will happen? Your whole reinforced structure will slide, right? That is called as base sliding, right? Whether it may be earth, water, seismic, surcharge. Limiting eccentricity, that is, there is a chance of overturning also. Overturning means it will fall down. Your retaining wall will fall down. That is overturning. So for this also check should be done. Next is the bearing capacity of the foundation. You have to also find out the bearing capacity of soil. You have to also foundation soil. We have also already discussed the foundation soil also we should test for the CN phi density, and then we can find out the bearing capacity of failure, bearing capacity of soil using the general shear failure or local shear failure. Settlement estimates you can also carry out. Immediate settlement. Consolidation means primary consolidation, and secondary settlement of the wall. Normally secondary settlement we cannot carry out, which we have discussed in consolidation chapter. So for these parameters should also be evaluated to control the external stability failure or external to maintain the external stability, these parameters should also be checked. So this is that steps. The seventh step is the reinforced soil wall drainage system. What does it mean? Suppose you are not going to provide the drainage facility in the retaining wall. There is a chance of failure. That means what? Subsurface drainage. That means inside the retaining wall, you have to have the drainage facilities. Otherwise, what will happen? The primary component of mechanically stabilized earth wall is soil. Water affects on this primary component of the soil. It can decrease the soil shear strength and increase the destabilizing forces. Then is the surface water runoff. You have to also provide the proper drainage facilities on the surface so that water will not accumulate. Otherwise, what will happen? It will infiltrate into the retaining wall and your wall will become weak. These are the design parameters for a soil reinforced structure, or this is also called as design consideration for a reinforced soil structure that we have completed. Now we shall go for the next topic, which is called as idealized soil behavior model. This topic was asked in the last year exam, right? So idealized soil behavior model means what? See, whenever we are going to construct any structure, whether it is a reinforced soil structure or a building or a bridges, whatever the structure we are going to construct on the soil, definitely there is a link between the soil and the bottom of the foundation, right? Soil have different nature, soil have different properties, and your footing of the foundation have different properties, right? And one thing I would like to tell you that whenever we are going to construct the footing below the ground level, suppose you are going to construct a 2 feet depth from the ground surface. 2 feet by 2 feet, you are going to construct one column foundation, right? 2 feet by 2 feet, you have given the footing. So at one edge of the footing, right, below the one edge of the footing, the soil may have different nature, right? And at another edge of the footing, the soil may have different nature that we have discussed earlier, which may cause differential settlement. So how we can make the soil properties same, right? By using some softwares, using some models. What does it mean? If the soil properties at below one edge of the footing is different and below another edge of the footing is different, how we can make both the properties similar, right? That is called idealization. How the properties of the soil can be make same of one area, right? That is called as idealization. And there is one term which is called as soil interface behavior. That is called as foundation and interface behavior. In your syllabus it is given there. Foundation and interface behavior means how the foundation and the soil, which both have different properties, are going to have different behaviors, right? So we shall see stress-strain relations are the mathematical description of the mechanical properties of the soil at any particular time under any given loading condition. Stress-strain means whenever you are going to construct the structure on the soil, the stress is going to be going to be felt by the soil, and the soil is also going to consolidate, a strain is also going to be there. So a strain will also be there, you are going to apply the stress, right? The next paragraph says that the inherent complexity in the behavior of a real soil, inherent complexity. The soil is a complex material. The void is there, air is there, or water may be there, solid particle is there. Even the solid particles at one place, different type of solid particle will be there, which will be having different type of clay minerals, different types of rocks, right? Rock properties. So what it says that the inherent means hidden complexity in the behavior of real soil has led to the development of many idealized models of soil behavior, especially for the analysis of soil foundation interaction problems, right? That which I told you, that we have to make the soil with similar properties. That is called idealization. The generalized state-system relationship for soils don't represent even the gross physical properties of a soil mass. Gross physical properties means what? Suppose you are going to take a footing at 2 feet by 2 feet. As I told you that one corner of the footing or below one corner of the footing, the soil may be different, and below the another corner of the footing, the soil properties will be different. That's why what it says that the generalized stress system relations for soil don't represent even the gross physical properties of soil. Gross physical means the same property will not be there. One corner property will be different, another corner property will be different. The idealized models are observed to provide the useful tools for this. How we can make the properties similar at each corner of the footing, right? That is called as idealized model. So the idealized soil behavior reduces the analytical work. Analytical work means what? Suppose below one edge of the footing, soil quality is different. Below another edge of the footing, soil quality is different. So if you are using the models in such a way that the properties below the footing will become similar, in that case, this model will be more helpful. So what you say there reduces the analytical work spent in the solution of complex problems in geotechnical engineering. The idealization will depend on variety of factors. Whenever you are going to idealize the soil, you have to know the following properties. What type of soil is there below the base of the footing? Soil condition means what are the properties of the soil below the footing? That also you have to know. The type of foundation which you are going to construct. The nature of extent of loading, whether point load, infirmly distributed load. Method of construction, purpose and lifespan of the structure. For what purpose you are constructing the structure? What is the design life of the structure? The economical consideration. So these points you have to know for idealization. Idealization means to make the properties of the soil same below the base of the structure. So idealized model of soil foundation interaction is briefly projected. What is here? You can see the Winkler model. Winkler was the researcher. Winkler was the scientist. He developed one model. He carried out one research. What he said that what he assumed that the deflection W of the soil medium at any point of the surface is directly proportional to the stress applied at that point and independent of the stresses applied at the other location. That means what? You can see this figure. Q is the stress which is going to be applied by the footing, right? And soil behaves like a spring, like elastic materials, right? Where the spring constant K is given there. And what is W is the deflection, W is the displacement, W is the settlement. So what he says that if you are going to apply the stress on a footing, the settlement is there, the deflection is there, and that deflection is proportional to the what the stress or the pressure which you are going to apply on the footing is proportional to the deflection. Is proportional to the deflection. So qxy, xy, what is the x? X is the x and y is the dimension of the footing, we can say, right? In x direction and in y direction, in lateral direction and in the your what we can say in the x-axis, in x-axis direction, and then in y-axis direction. Z direction means depth, vertical displacement. So we shall see here q is the vertical contact pressure of the foundation, w is the settlement, and k is the foundation modulus, or called as coefficient of subgrade reactions, right? You can see in the second figure also, w is the deflection. So whatever the Winkler said, that when you are going to apply the pressure or stress on the soil, the deflection, it is proportional to the deflection. You can see one important feature of the soil model is that the displacements occurs immediately under the loaded area. What is the important thing? Outside this region, the displacement are zero. That means what Winkler said, that suppose you are going to construct the column foundation on the soil, it says that whenever the stress or the pressure on the column is going to be applied, directly vertical displacement is there. Adjacent to the footing or beside the footing, whatever the soil is there, those soils are not going to feel any type of stresses, right? But normally, if you are going to suppose you are going to apply the pressure on a column, whatever the soil is there adjacent to that, they are also going to feel the stress. But Winkler said that directly vertical displacement is there, right? And soil acts as a spring, right? And the vertical the horizontal direction, that means outside the area of the footing, the stress is not going to be experienced by the adjacent soil. You can see here outside this region the displacements are zero. You can see the springs, you can see the loading. The first loading you can see non-uniform load, displacement is directly below the ground level. Beside this, the spring is just like that. There is no, the spring is not going to be not going to shrink, right? Due to the application of load, the side springs are not going to settle. That is the idea of the Winkler model. Even in the point load also you can see. You can also see the rigid load. You can also see about the flexible load. So also the displacements of a loaded regions are constant whether the soil is subjected to infinite rigid load or uniform flexible load. For any region, wherever you are going to construct the soil, construct the structure, any structure, or any type of a structure, whether it's rigid structure or the flexible structure on the same soil, the displacement will be same. This idea was given by the Winkler, and this is called a Winkler model. So this question was also asked last time, right? You can see the last year question paper asked by the Dr. APJ Abdul Kalam Technical University, Lucknow. So what we can say, some limitations are there for these models. Limitation means some advantage and disadvantage, both is there. What are those points? This model is easily adopted by computer program, which makes the calculation in a very short period of time, right? But which data you have to use? We have already discussed the soil condition, the type of structure, the type of soil, right? All the data we have to know, and that data we have to put in the softwares Then we can find out the how much displacement will take place. The idealization is simple and accurate. This idealization model, it gives excellent results with field observed data. Whatever the data you have collected in the field, you have analyzed, type of soil, type of the structures, it will give you good results. Compared to finite element method or model. Finite element method or model, actually finite element method models are there. Many models are there like UDEC, FLAG. Those models depend upon the finite element models. The spring model means Winkler model. This is called a spring model. Uses a rather simple model that requires fewer parameters and less calculation time than finite element method model. Right? It needs some data, less data, and less time for the calculation. For a load acting on the spring affects that particular spring only, while in reality, soil is continuous medium and the interaction between them soil to soil do exist. This is the drawback we can see. What I'm trying to say here, what he says that below the base of the footing, at every corner, by using this model, the soil is going to behave same, behave same, and the displacement will only be below the base of the footing, not the displacement is not going to take place in the adjacent areas or in the surrounding area. That means the surrounding area of the soil, right? Surrounding area of the soil of your footing is not going to feel any stresses, which is what we can say, which may not be the correct, right? This may this we can say the disadvantage also, and this is the limitations. So this is all about the your today lectures, and I would like to tell you that unit 5 we have completed today, right? And in the next lectures we shall go for the clearing the doubts. We shall also solve some numericals, right? And this is all about your today lectures, and unit 5 is completed. Thank you very much.